Like was just said, my name is Doug Archer. I work at the Johnson Space Center in Houston, Texas. I graduated from here in 2004 with a bachelor's in physics, actually in 2010 from the University of Arizona with a PhD in planetary science. And I'm happy to be here with you guys today. What I want you to get out of this is first to learn something about Mars that you might not have already known and some of the things that we've learned about Mars in the past 5 years. I hope that you think that's cool, and I hope that at least some fraction of you see how this is relevant to you as biology students. But hopefully, I hope that you just find this interesting at a general level as well. So this is Mars. This is a beautiful picture of Mars. You see the Valles Marineris, the largest canyon in the solar system, cutting across the middle of Mars right here. The Grand Canyon could easily fit inside of that multiple times. It's so large that if you were on one edge of the inside of the canyon, you couldn't see the other edge of the canyon. Mars is, so some fun facts about Mars, it's about half the radius of the Earth, a tenth the mass, 40% of the gravity. It is 1.5 astronomical units from the sun. The Earth is 1 because astronomers are lazy and like to define things in very small numbers. The Martian day, so about that means that at its closest, Earth and Mars are about 0.5 AU apart, or 50 million kilometers or so. And at their farthest, they can be 2.5 AU apart, so completely on opposite sides of the sun from each other. That's something that I care a lot about a lot, because when we are commanding the rover, when they're really close together, it's a 4-minute light time delay from Earth to Mars. When they're on the completely opposite sides of the sun from each other, that's actually called solar conjunction, and I get a month off because the sun is in between. We can't talk to it, so the rover just kind of chills on Mars for a month. But when it's at its farthest, it's a 20-minute round trip light time delay, and that impacts how we do operations. So if you might have a view in your mind of, if you're driving a rover on Mars, that means sitting in front of a computer screen with a joystick watching a TV. But really what we do is we do things we plan things at least a day at a time. It can be 1 day, 2 days, or 3 days at a time. So we'll plan an entire day, and then we come back the next day on Earth when the rover has already executed everything, the rover's gone to sleep, and then we plan things for the next day, or we call them a sol on Mars. So Martian sol is 40 minutes longer than an Earth day. That's just kind of by chance. There's no reason for it to be like that. The Martian year is about just under 2 Earth years. So we've been on Mars now for 5.5 years, so that's about 2.5 Mars years. The obliquity of Mars, or the tilt on its axis, is about 25 degrees. That's very similar to the Earth's, which is 24 degrees. That's important because that means that Mars has seasons like we do on the Earth. And right now in the southern hemisphere of Mars, which is where Curiosity is, it is winter. We're about to come out of winter. The temperature range, Mars can get very cold, minus 130 degrees C, colder even than Antarctica. But at the surface, at the equator, which is where, again, MSL is, it can actually get up to 20 degrees Celsius, or that's around 65 degrees Fahrenheit on the surface. But Mars has such a thin atmosphere, it's only 7 millibar, that the atmosphere can't really hold heat very well. So the surface can be 20 degrees, so your feet could be 20 degrees C, and your head could be like minus 30. So there's a huge temperature gradient between the surface and as you go up into the atmosphere. So it's a very different place. The atmosphere is 95% carbon dioxide, 2% nitrogen, 2% argon, and then some trace gases. So I work on the rover, the Mars Science Laboratory, nicknamed Curiosity. Curiosity's primary scientific goal is to explore and quantitatively assess a local region on Mars' surface as a potential habitat for life, past or present. So we do that by assessing the biological potential, the geology and geochemistry, water, weather, and climate, and we also look at radiation levels and potential hazards from radiation. So a little bit about Curiosity. This is Curiosity inside of a heat shield and back shell. So that's where, after you launch, that's what it's going to look like as it's traveling to Mars. There's some little solar panels on there, so we have electrical power as we're traveling to Mars, as it's kind of cocooned inside of its heat shield and back shell. This is the rover itself down here. With the wheels extended and the mast, the thing sticking up from the deck, extended as well. During landing, the wheels were tucked up underneath, and the mast was folded down so that we could fit underneath this descent stage up here that you see in the top right. So this was the first time this landing system had ever been used, so you can see that we don't have any rockets on Curiosity. The rocket motors are all on the descent stage, And so I encourage you, don't have time for it today. There's a video on YouTube you can go look for called 7 Minutes of Terror, which it really was, that shows how this landing happened. And it's really cool. So we go from something like 18,000 miles an hour down to the surface in 7 minutes. So you have to very quickly shed a whole lot of energy. And the way that works, so first of all, we launched from Cape Canaveral in Florida on November 26, 2011 on the top of an Atlas V rocket. Got us going to Mars, so we cruised until August 6th of 2012, at which point the cruise stage separates. We actually did a little bit of guided entry, the first time that's ever been done on Mars, which gave us the ability to land a lot more precisely. We go through peak heating, so this is where you're really using your heat shield, peak deceleration, flying around a little bit. The parachute pops out. I'll show you the parachute in just a second. Then a little bit after that, you don't need your heat shield anymore. The heat shield pops off. You have a radar on it that acquires the ground, so you know how far above the ground you are. And then, because Mars's atmosphere is so thin, a parachute can't actually slow you down enough to safely land on the surface. So we have to cut ourselves free from the parachute. The parachute and the back shell go and crash somewhere else. Our rockets turn on, and the first thing it does is get out of the way of the parachute really quick. So it diverts quickly over to the side so that the parachute and the back shell don't come down and hit it. And then we do a relatively slow descent to the surface. But where this landing system was unique, the engineers were saying, this is going to be a really long-lived mission. We don't want to be carrying around with us fuel tanks that are potentially full of rocket fuel and rocket engines for multiple years. So they designed the descent stage to be separate from the landing stage. I think the clicker just died. We'll just use this. So again, in the top right, that's the descent stage. So the descent stage had a winch. It was connected to Curiosity with a winch. So when we got close to the ground, it starts lowering the rover with the winch. The wheels have sensors on them that can say, okay, we've touched the ground. When that happens, an explosive bolt fires, cuts the winch. The descent stage flies off and crashes in the distance. The rover, the mast comes up, we wake up, and we took our first picture. And I love this. It was just fun to see. We're all looking at the picture like, what is that? The first picture we saw from Mars, there's this big kind of plume in the background. And we pieced together that, oh, that's the descent stage exploding. Like, we had enough extra fuel, because you always want to take more than enough in case something goes wrong. We had enough extra fuel that the first picture we took from Mars was the descent stage exploding in the background. Very Hollywood-like. So this is a parachute test, just to give you a sense of scale of the parachute. So there's the parachute. This is a person for scale. So really big parachute, but this can't slow you down enough on Mars to just safely land. Like on the Earth, right, astronauts land with just parachutes. It's okay. Parachutes slow you down enough. On Mars, you can't do that. This is a picture. So we have a camera on the bottom of the rover. So as soon as the heat shield popped off, we started taking video of the descent. And these are just a couple frames from that. So this is right after the heat shield separates. You can see the heat shield falling away. And this is right before we're starting to land. So you can start seeing the rocket exhaust impinging on the surface and blowing stuff away. And we actually made marks that you can easily see from orbit. This is just really cool. So this was taken by a camera on the Mars Reconnaissance Orbiter. The camera is called HiRISE, built at the University of Arizona. Go Wildcats. And so MRO, the orbiter, was relaying information of the landing. So MSL is communicating through the orbiter to Earth. It also took a picture during landing. So this is an actual picture on Mars of MSL hanging from the parachute as it is descending to the surface. And that, every time I look at that, that gives me chills. That is just an absolutely amazing engineering feat. So some fun facts about MSL. We have the rover itself, so not including the descent stage. The rover itself weighs 900 kilograms. It's about the size of a small car, so think kind of like a Mini Cooper. It's pretty big. But that Mini Cooper has a 100-watt power supply. It's a chunk of plutonium. As the plutonium decays, it gives off heat. The heat is converted to electrical energy. That provides 100 watts of energy that is slowly decaying over time. That means our big power supply, which is the big white thing on the back of the rover, that could power one 100-watt light bulb. That's how much power we have. That's what we use to drive around. That's what we use to take all of our pictures. That's what we use to communicate with Earth. That's what we use to drive. all the power that we have. Now we can play a little bit of tricks because we don't draw power directly. The power, or the radioisotope thermal generator powers or charges a battery, so you can use a little bit more than 100 watts at a time. But we are very power limited by what we can do on Mars. The reason that we don't use solar power, which can be a little bit, we would have like giant solar panels, and then the problem is Mars is very, very dusty. You get dust deposition all the time. So having a nuclear-powered rover allows you to go more places on Mars and be, like we know when we're going to run out of power. With solar power, you're not really sure, but people ask that. So another fun fact, our top speed is 4 centimeters per second, which means we could be outrun by a very engaged turtle. So that's, again, to show you that we're not exactly tearing up the ground there on Mars. So this is just a little bit about the instrument package. We have a number of different scientific payloads with us. We have a DAN that looks for subsurface hydrogen, a weather station, a number of different cameras. ChemCam is really cool, the chemistry camera. You can see the red line from there, that's a laser. So it has a high-powered pulse laser that can shoot rock up to 5 meters away. It's high-powered enough it creates a plasma. We've actually taken pictures of this on Mars. It's pretty cool. Like you see these really bright flashes. And the plasma, or the color of the plasma, we have a spectrometer. That's the Cyclops eye, is like a telescope connected to a spectrometer. So we can tell the chemistry of a rock by zapping it with this rock, or by zapping it with our laser. And we use that all the time. We've done something like over 1 million shots of the laser, or different spots that we've hit with the laser on Mars. The RAD instrument to look for radiation. APXS does more precise chemistry. MOLLE, which is a camera at the end of the arm. Then we have a drill, scoop, brush, and sieve to acquire and process sample. MARTI is the camera pointing down. And then the two instruments that I work the most with are the SAM instrument, or the Sample Analysis at Mars instrument, or the chemistry instrument, or CheMin instrument, Chemistry and Mineralogy. CheMin is an X-ray diffraction instrument. So if any of you have ever done X-ray diffraction, it does definitive mineralogy. So it can tell you, it's looking at the crystal patterns in the rock, so it can tell you, oh, that is exactly this mineral. And that is important because a lot of minerals have a very narrow range of temperature, pressure, and water to rock ratio that they can form in. So if you want to know about the past environment on Mars, right, like we didn't have weather stations 3.5 billion years ago, but we have rocks from 3.5 billion years ago. So we look at the rocks, and the mineralogy of the rocks can tell us what the environment was like. And that should be important to you guys because, life can only exist in certain environments. So if you want to know whether or not an environment is habitable, 3.5 billion years ago, one of the easiest, or one of the most robust ways of doing it is looking at the mineralogy of the rock. SAM is an instrument about the size of a microwave oven. It weighs 80 kilograms and costs $110 million. It's a very expensive microwave oven. But this is kind of like an entire room-sized laboratory condensed into the size of a microwave oven. Like I was at the Goddard Space Flight Center yesterday, where they have the mock-up of this, and we were talking about how everything in that room that you would use in a terrestrial lab was all miniaturized to fit into something the size of a microwave. Like for example, you might, if any of you work with gas bottles, you have like K bottles full of gas, or think of like helium balloon tank that'll be like about as tall as I am, and you'll go through those fairly frequently. At least in my lab, we go through them every few months. We have 2 on Mars that are this big, and they've lasted us for 5.5 years so far, and will last us for until the rover dies. We're never going to run out of helium. They have 6 gas chromatograph columns, a quadrupole mass spectrometer. So what we do here, we deliver the sample through the 2 red ports in the top. Those stick out the top of the rover deck. So we have these covers on these. You open a cover, you deliver sample into it. It goes into one of 2 ovens. You heat up the sample, and the gas is passed to a mass spectrometer, or goes to a trap for a gas chromatograph. So then you heat up the trap, and they can get sent to the GC column. So you're looking for inorganic volatiles such as water, oxygen, carbon dioxide, sulfur dioxide, or organic molecules with the gas chromatograph, or in the regular EGA mode as well. So the other one that I'm going to talk about a little bit later is the TLS, or tunable laser spectrometer. This instrument also has, there's 2 different inlets from Mars, so we can also analyze the Martian atmosphere with that, and that's going to be important in just a second. This image is just really cool. This is a this is a mosaic of images. So this is our selfie on Mars. We've actually taken a number of these. We take them usually every time we drill. And so a lot of people, well, how did you take that? There's no arm or anything. And so that's because this is actually about 50 images that have all been stitched together. And we do it in a way that we can crop the arm out of the images. But this is a real picture of the rover on Mars. And I just think that's really cool. Okay, so let's back up a little bit and talk about what is habitability. So first, let's assume that we're talking about Earth-like life, because if any of you have ever been to an astrobiology conference or anywhere where you're talking about the definition of life, if we got into that, we would be here for weeks and would have made no progress. So we're going to just assume that when we're talking about life, we mean Earth-like life, and go from there. So we know that life requires water, requires energy, water or some solvent, let's just say water, energy, essential chemicals such as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. And you have to have a benign enough environment so that the rate of growth or repair is greater than the rate of destruction or death, right? So if you're in an environment where your destruction rate is higher than your growth rate, life is going to go away very quickly. So what do we know about Mars and Mars's habitability? So present-day Mars is cold, it's dry, has no ozone layer, so you get shortwave ultraviolet light down to about 195 to 200 nanometers down right to the surface. There's no magnetic field. So the Earth's magnetic field protects us from all of these high-energy particles in space, right? Like that's what the aurora borealis is the high-energy particles getting trapped in the magnetic field interacting with the Earth's atmosphere. Mars doesn't have a magnetic field, so you get high-energy ionizing radiation all the way down to the surface. So the top meter or so of soil or Martian surface, within 100 million years, you're going to alter any kind of organic. There could still be organic there, but if you're talking about like molecular biomarkers, they're going to be altered within about 10 to 100 million years. So in the immortal words of Elton John, and you guys might not know this song, Mars ain't the kind of place to raise your kids. But what about the subsurface? Maybe. And what about Mars's past? So we know that Mars used to be much wetter, that we have abundant evidence for river channels, lakes, and potentially an ocean. The image in the top right here is an image of river channels, and these are big. The crater, so the circular feature in the lower left, that's at least 150 to 200 kilometers across. So these are large river channels. Down on the bottom, this is an image from Curiosity, and you see these layers here, and I'm going to show you again later. These layers, these sedimentary rock, was laid down at the bottom of a long-lived lake. So we know that Mars was a more habitable place in the past based on what we've learned from these missions. And the question is that we're going to keep talking about is, okay, so just how habitable is it? But then Mars, at some point in the past, about 3 billion years ago, experienced planet-wide climate change, where it went from warmer and wetter, potentially having an almost hemisphere-covering ocean, to cold and dry, where the only water really on Mars today is in polar caps or buried glaciers or ice-cemented soil. There's essentially no liquid water on Mars that we know of today. So we underwent at the surface, maybe deep down. So we underwent this huge planet-wide climate change at some point. So how did that happen? So we landed in a place called Gale Crater. The way this works is, it's actually kind of interesting the way we choose a landing site. Anybody can propose a landing site. You have landing site workshops. Anybody can come to a landing site workshop and say, hey, I really like this place on Mars for this and this and this region. Anybody can propose. And then there's a big room like this full of people who will get up and say like, well, that one's not good because of this, and this one's better because of whatever. We ended up settling on a place called Gale Crater, which is a 150-kilometer wide hole in the ground, 5 kilometers deep, with a 5-kilometer high mountain in the middle of it called Mount Sharp. So Gale Crater sits right on the north-south dichotomy boundary on Mars. This is a shaded topographic relief map on Mars, with the reds and oranges being higher elevation, the greens and the blues being lower. So if you'll notice, there's a lot of red and orange in the southern hemisphere of Mars, and Mars is a little bit tilted in this image. And then the northern hemisphere is very relatively low and smooth. If I zoom in, there's craters all over the place because it's not Earth. but much smoother. And that's where there might have been an ocean in Mars's past. So we landed in Gale Crater, which is a crater right on that dichotomy boundary. So Mount Sharp, right in the middle of the crater, is 5.5 kilometers high. So for scale, I added Mount Timpanogos. So Mount Timpanogos, 3.5 kilometers high. Vertically it's to scale, horizontally it's not. Mount Sharp is much broader at its base than Mount Timpanogos. But that's just, again, compared to, Mount Sharp is larger than Mount Rainier. It's almost as high as Mount McKinley, and it's a little more than half as high as Mount Everest. Like, this is a large mountain. It's something that I think you guys appreciate. I live in Texas. The highest point in Houston is probably like a freeway overpass. So when I talk to people in Houston, they have no real appreciation for, like, 5-kilometer high mountain is really, really big. This is just kind of a side view of that. So what we're trying to do, and what we knew from orbit, is that this mountain, so when craters are formed, you frequently have something called a central peak. This actually does have a central peak as well. You can imagine if you drop something into water, you have a bit that splashes back up. The same thing happens, it turns out, when you hit rock with an incredibly fast-moving projectile. You hit the rock, you excavate a big hole, some of it actually pops back up, forming a big central peak. So Mount Sharp has a central peak, but then the rest of the mountain is built around that central peak, and we could tell from orbit that these were sedimentary layers that were changing as you were going vertically. And what we knew from before, so what we're trying to answer, and I'll show a slide from the ground, what we're trying to answer is, so how did Mars go from a place like this to a place like that? From this to that. So this is one of the first pictures we took of just a portion of the mountain from the ground. And so you can see the paintbrush unit, it was just kind of a feature that the morphology that somebody named it the paintbrush unit. Then you have hematite ridge, so an iron oxide rich ridge. We're actually sitting on top of that right now. And then we have the clay unit and the sulfate unit. So clays are formed when Mars is warmer and wetter. Sulfates when Mars was cold and dry. So we went across this boundary, or this mountain straddles the boundary from warmer and wetter to cold and dry. So that's why we chose this place to land, and that's what we're trying to explore. This is just a really cool picture. It's kind of tiny on the screen, but if you go to the MSL website, you can zoom this in or zoom in on this at the full resolution. It's really cool, but it shows essentially where we landed over to the right by Yellowknife Bay, and then a little white line is the whole our whole traverse to this point. And this is just looking at the orbital view. Again, landed in the top, and then have been moving to the southwest ever since. Yesterday on Mars was Sol 1985. That's about where we were, and we have driven 18.231 kilometers as of, again, yesterday. I think we drove 30 more meters or so last night. So again, talking a little bit about the sample analysis at Mars instrument. Like I said, one of the things that we can do is actually ingest a little bit of Mars atmosphere and look at the atmospheric composition. And one of the things that the TLS saw, one of the things that we can measure, we can very sensitively measure methane. Methane, simplest organic molecule, something important to look for. We've seen two things. One is that the background of methane, which is at about the 1/2 of a part per billion level. So we're not talking about a lot of methane. This is a very, very trace gas in the atmosphere, 1/2 of a part per billion. It changes seasonally. That we still don't understand. We're trying to figure out why that happens. What was more exciting was that about on Sol 300 and then around Sol 500, we saw a big spike in methane, which again, big is relative. It went from 1/2 of a part per billion to about 10 parts per billion. So it's a factor of 10 or 20 difference. So it's a big change, but in absolute terms, it's a little bit of methane. But the reason why this is exciting is that methane, a spike like this, means that Mars is, in some sense, alive. Because methane can really only come from one of two ways. One is life, right? Like we have methanogenic bacteria, organisms that can actually produce methane, and we might be seeing evidence of that. However, this isn't a slam dunk for life because there is also a geologic process called serpentinization, where you combine olivine, which is a volcanic rock, warm olivine with water, and that can create methane as well. But that in and of itself is exciting because we can say in one way or another, Mars is alive. It's either still geologically active on some level or there is life somewhere that's producing methane. And the important thing again about this, if you have rock and water, I mean, even if you're a few kilometers down, if life ever evolved on Mars, that would be a great place for life on Mars today. So this is really important in terms of quantifying Mars's habitability. The other thing that we can do with MSL is collect solid samples. So this is an image of the arm down with the drill out. You can't see the drill here, but trust me, the drill is out drilling into the sample. And then in the background here, you can get kind of a sense for it. So that's like the whole mountain. So that thing is huge. You know, it's 5 kilometers high and like 80 kilometers across. This is a very, very, very large mountain. And this is, we're at the base of it here, and we've been kind of climbing up the mountain ever since. So and this is that drill hole. So we have a drill that's about 1 centimeter diameter, 6 centimeter deep. So we're really only literally scratching the surface of Mars. We're going this deep. It collects sample. You can see the image in the bottom left. That's some of the sample in the scoop. One interesting thing about Mars is that Mars is the red planet, right? Like the whole planet looks red. That's because of, in some places the rocks really are red, but the whole planet looks red because you have this really bright red dust that coats everything. And a lot of things, like we have a brush that we take with us, so like a stainless steel brush that you spin really fast and it brushes off the surface. And a lot of rocks, when you clear them off, they're not red, they're actually gray. Or you drill into them and it's gray. And the reason again that's important is that red is generally oxidized iron and gray means more reducing conditions. And so that is that's important in for a number of different reasons for habitability or for life. This is a close-up taken with the MOLLE camera at the end of the robotic arm of a drill hole. And this is really cool. I like showing this to show how great some of the engineers that I work with are and some of the precision that we have with. So you can see in the back of the drill hole, there's kind of this white thing going up. That's actually a sulfate vein in the rock. We'll talk about that a little bit later. But just to the right of that, do you see like a series of little dots going up the wall? Those are the laser spots. So that we can target something this big, a meter or so away, with millimeter precision, and hit somewhere inside this drill hole and walk up the drill hole wall a millimeter at a time. And so we can tell you like, oh, and one of these, like the second one up, you can see kind of hit a vein, and you can see that in the data. Like, oh wow, we got this big sulfur spike. Yep, there it is. It's right on top of this vein. That to me is just really cool and shows the engineering prowess of the folks that I work with. So back to mineralogy. So CheMin uses X-ray diffraction. So you're shooting X-rays through a sample. It diffracts. It makes these circular patterns. You integrate over the circular pattern to get the two-dimensional X-ray diffraction pattern that you see in the top right. And that is telling you definitive mineralogy, where that is important. If you see here where it's labeled phyllosilicate, this is where we've discovered clay minerals on Mars, and some of our samples have 30 to 40% clay minerals in them. That's a lot of clay. That's really important for a number of reasons. One of the first one being clay. Clay is a weathering product of other rocks, and it requires water at relatively neutral pH to do it. So this is another of those kind of indicators that we have to tell us about habitability, that we can say that, hey, we have clays, and we can tell you the particular type of clay it is. This is like an iron-bearing smectite clay for anybody who cares. And that we can say like, okay, that was formed at a pH of like 5 to 7 at a water-rock ratio where there's enough water that if you were a little bug living on Mars when this happened, you would have been perfectly happy to live in that environment. With the sample analysis at Mars, like I said, we heat the sample up, so temperature on the x-axis, signal on the y-axis, and we can look at the water coming off, carbon dioxide, oxygen, sulfur dioxide, hydrogen sulfide, hydrogen, and the high temperature water peak at around 750 degrees, that's also indicative of the clay dehydroxylating, so that's more evidence for the clay. But at lower abundances, we also see organic molecules. So we have detected organic molecules in Martian materials before. So it turns out that there is a small chance that when a meteorite hits Mars, there's a big impact. Some of that material actually reaches escape velocity and goes out of Mars orbit. There's a very small chance that some of that material ends up on the Earth. So we have about 30 to 50 Martian meteorites, so things that made its way somehow through space to crash land on Earth. A lot of them come from Antarctica or were found in Antarctica. So we actually do have samples or pieces of Mars that have been delivered to Earth. We've looked at those samples. We found organic molecules in some of them before. This is the first time that we've ever seen organic molecules in Martian samples on Mars where we know where the sample was. The problem with the meteorites is we don't really know on Mars where they came from, how deep they were, what might have happened to them before they got ejected from Mars. So this was a really important measurement because, again, you guys know this, I don't have to tell you this, organic molecules does not mean life, right? But it's kind of the building blocks for life. If you want to have life as you know it, you have to be able to have organic molecules either as kind of a food source or be able to preserve organic molecules to use in your biochemistry. In another drilled sample named Mojave 2, we found mass fragments consistent with C1 to C4 alkanes and single ring aromatic compounds. We also found sulfur-bearing organics such as dimethyl sulfide and thiophene, which was interesting. This was a very sulfur-rich rock, so there's some kind of interplay between the sulfur and the organics as well. And this is data that's been presented at a couple conferences and is under review right now in a journal. So where do these organics come from? There's two options, abiotic or biotic or biological processes. Abiotic processes, so it turns out that igneous processes we know can actually create organic molecules. It's kind of cool how that can happen. There's also meteoritic infall. In the bottom right, so the top right is a meteor shower. You could go and see that many times a year here on the Earth. The bottom right is a piece of a meteorite called the Murchison meteorite, which was collected, I think, in 1970 or something like that. This is a type of meteorite called a carbonaceous chondrite, which is a very, very common type of meteorite. And these meteorites, so this rock has over 10 weight% organic carbon in it. And it has a huge variety of organic molecules, including all of the amino acids that are used in life. So this is something that is very relevant to the origin of life. People talk about, how did this whole process get kickstarted? And one of the ideas out there is that you actually have extraterrestrial input of organic matter through materials like this. And this kind of thing, there are billions of tons of this getting deposited on the Earth every single year. So this is happening all the time. Another kind of geeky biochemistry thing, in case you care, that one of the things that they found in the Murchison meteorite, one thing that is kind of problematic in the origin of life, or one thing that we're trying to understand, right, is okay, how do you go from a racemic mixture or chiral parity where you have equal amounts of left-handed and right-handed things to a biological system where you only use one or the other, right? Left-handed amino acids and right-handed sugars. So it turns out that there is a slight enantiomeric excess in the amino acids and sugars in one direction or the other in the Murchison meteorite. And so one idea is that you have this enantiomeric excess delivered to Earth in these meteorites, and then there's some kind of process on the Earth that amplifies that as you move towards the origin of life. So these are the kinds of questions that we're also trying to address by looking for life on Mars. So what did we find at Yellowknife Bay, the very first place that we went? We found that the regional geology and fine-grained rocks or mudstones suggested that the site that we called John Klein was at the end of an ancient river system or within an intermittently wet lake bed. Like I talked about already, the mineralogy indicates interaction with liquid water that wasn't too acidic or alkaline, had low salinity, and the conditions were not strongly oxidizing. There were key chemical ingredients for life that were present, such as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. And we had the presence of minerals in various states of oxidation, which would have been a fantastic energy source for any bacteria that might have been there. So this is just building out that story a little bit more. This is another really cool orbital view where if you look closely there, you can actually see the rover tracks, and where there's a circle, that's where we stopped and did a donut. Really? There's a reason they do that, but that's actually what that is. And then the rover itself is down here. And so the next picture was taken at this location. So this is called Winjana. So here we have another set of sedimentary rocks, and we've been seeing this over and over and over again as we've been climbing up the mountain. So that, and then here's some more here. And this is a schematic showing what we've been seeing. So As you have a river that enters into a standing body of water, it creates a delta. As material falls out of the river in suspension, you get the coarser material first and the finer material second. As the river or the delta progrades and the lake levels rise and fall, you get successive patterns of these strata or sedimentary rocks. And that's what we've been seeing over and over and over again as we've been climbing up the mountain. I mean, this is exactly, we have a lot of terrestrial geologists on the team, and they'll show you, like, here's what it looks like on Earth, here's what it looks like on Mars. It's the same. And we know that that existed based on the sedimentary sequence. That lake existed for at least 1 million years, maybe up to about 10 million years. So that's quite a long time, but we can push it even farther than that. So what happened is you form these rocks, you form these sedimentary layers, they lithify into rocks, they fracture, and then you have fluids that are bearing a different composition come through. So if you look in this rock here, you see all this white stuff. Those are veins. The white stuff is calcium sulfate. So you have calcium sulfate-rich water flowing through these veins that then slowly precipitates out. And we've been able to date some of this stuff to 1 to 2 billion years after the lake. So that means that you could have water present at this location for up to or more than 2 billion years. So quite a long time. This is just a picture of all of the drill holes that we've drilled to date to show kind of the variability. Just from the color, you can see what some of the variability is. And here, this is just a pie chart of the mineralogy. Pay attention particularly to the green, where you see a lot of, that's the phyllosilicates or clay minerals. See a lot down here in Yellowknife Bay, what we've already talked about, goes to a little, and then you have some more oxidized, altered samples where you actually have a lot of silica, which was interesting, and then up to samples where you can have up to 40% clay. And that's a lot of clay, meaning highly altered, those rocks saw a lot of water. Okay, so what have we learned? So we're really just starting to piece together the history of Gale Crater. We know that the crater was formed about 3.5 billion years ago. It had a series of lakes and streams that persisted ephemerally that laid down quite a bit of sediment. After lithification and burial, you had the fracturing and aqueous diagenesis by fluids bearing calcium sulfate or other chemicals in solution that persisted for at least another billion years. So this is definitive evidence for water at this location on Mars for 1 to 2 billion years. So Gale hosted this lacustrine system, the one system that persisted for at least 1 million years. The water was fairly neutral and contained all the chemical ingredients for life. Another interesting thing is that as the lake levels rise and fall, and then you have the atmospheric and mineral interactions and different mineralogical inputs, you're getting diverse mineralogical inputs into this area where you have things that are oxidized and reduced. You have a lot of different minerals which would be great for an energy source for Earth-like life. Like, so for example, I think, is this on my next page? Yeah, so potential energy for life, we've seen sulfur and sulfate. There's bacteria that reduce sulfur and sulfate. Perchlorate, we have perchlorate reducing bacteria on the Earth. We have seen evidence for hydrothermal systems, which generally have very large chemical gradients that life takes advantage of. Going back to the top, we've detected organic molecules on Mars for the first time, but with the caveat that we know that the radiation environment destroys a lot of stuff or alters a lot of stuff in that top meter, so that we really need to get deeper down. And then we've detected variable methane in the atmosphere, which again is really important because it means that at some level Mars is alive. It means that it's either from life or there are environments geologically that are still active today, which would be a great place for life to live if it ever did evolve on Mars. One final note, photosynthesis would be a little bit rough on Mars unless you have sunscreen. But that's actually something that I worked on with Dr. Allred as an undergrad here, is looking at, there's actually iron oxide is kind of like a natural sunscreen. It absorbs UV light. So there are ways that you could make that work, but photosynthesis as an energy source is a little difficult on Mars. So implications and future questions. So were there specific locations, or there were specific locations on Mars that were definitively habitable 3.5 billion years ago. So, and we're really looking for a second genesis of life on Mars that can help us to understand the origin of life in general, and if the exact terrestrial biochemistry that we have on Earth is necessary, or if it's just one potential pathway. And I mean by that, right? Like, does it have to be DNA with these 4 particular bases and these particular 20 amino acids, Or can it be something else? Like, is that just how life happened to evolve on the Earth, or does it really kind of need to be that? And getting another data point, right? Like, this is kind of the astrobiologist struggle, is that you have a statistical sample with or a data set with a sample of 1. So it's hard to know kind of in general, making extrapolations from that, and looking for a second genesis on life on Mars can tell us a lot about the potential origin of life. And then another kind of open question that we need to know more about is, can biomarkers from 2 to 3 billion years ago, molecular biomarkers, persist on Mars to today in the near surface environment, or do we need to probe the subsurface? And so before I wrap up, I just have a couple quick pictures that I want to show you. 2, because like these are beautiful pictures, but also like not just in Utah, but when I show these, a lot of people are like, that just looks like southern Utah. And I think, that one, and particularly this one, it's like, there's the mountain biker in Moab running around there. But this is on Mars, just this beautiful location in Mount Sharp with all of this beautiful topography. And then for a little bit of perspective, this is an image taken by Curiosity, the Mastcam instrument on Curiosity, a little bit over 4 years ago. And if you can see, there's a tiny, tiny little dot there. And then if you zoom in, that's the Earth and the Earth's moon as seen from Mars. So that's, I love looking at that image to give us a little bit of perspective, and I love working on Mars about every day, and I hope that you found something that's applicable to you, and there are really a lot of opportunities in NASA for biology. NASA does a lot of astro or exobiology. We talk about habitable worlds, all this kind of stuff that if you're interested in, I'd be happy to talk to you about it, but that's what I do, and thanks for listening.
Questions for Doug? You want to just call them out?
Yeah, sure.
So with surface water, does that suggest that there had to be a thicker atmosphere to have the partial pressure and actually?
Yeah. So the question was, does thicker or surface water require a thicker atmosphere? And the answer is absolutely yes. Mars, because Mars is smaller than the Earth, it's easier for it to lose gas from the atmosphere. So Mars definitely had higher atmospheric pressure in the past. We still don't know how. Nobody's been able to come up with the right mix of pressure to get Mars to be warm enough to have this. Because, for example, generally we think that it had a lot more carbon dioxide, like 1 or 2 bars of carbon dioxide in the past. But if you start going more than that, carbon dioxide, it actually reaches a point where the kind of greenhouse effect peaks and then starts going down in the other direction. So, but yes, Mars definitely had to have had a thicker atmosphere in the past. Yeah.
Do you look at isotope bias for the methane to find out if it's biological origin or not?
Yeah, so the question was, do we look at the carbon isotopes in methane to see if it's biological or not? And the problem is the methane is so low abundance that we can't do isotopes on it. Like, we are just at the detection limit for methane. We do look at the carbon isotopes for, so I showed earlier, every sample that we have analyzed releases carbon dioxide. So we look at the carbon isotopes in the carbon dioxide as well as in the sulfur. We can look at the sulfur isotopes. And that is something that we have seen things that are suggestive of the carbon isotopic fractionation that you might see in biological systems on the Earth, but nothing that's like an absolute slam dunk. But yes, we do look at that. Yeah? How deep is the regolith on Mars? That kind of depends on what you define as regolith. It's a lot more indurated than on the moon, so just the loose stuff. And well, in some places, just a millimeter. Like, it's a very, very thin covering on top of a really, really thick rock column. In other places, it could be tens to hundreds of meters deep. But yeah, it's kind of a nomenclature thing, what you define as regolith. But yeah. Other questions? Yeah.
Is NASA training or planning for a manned mission to Mars, and if so, how long would that trip take?
So the question is NASA planning for a manned mission to Mars, and if so, how long would that trip take? So I work at the Johnson Space Center, which is the Human Spaceflight Center. So yes, we are. There are things here that I'm doing that are directly applicable that I work with the human spaceflight folks. Like, they want to know if you heat up Mars soil, how much water comes from it, because they don't actually want to use that. Like their plan is to, like, we're going to take little tractors with us or little mining equipment, and we're going to go collect sample and heat it up to collect water, because it turns out that it's actually more efficient to do that than to bring everything with you. So we are looking. NASA recently has, the focus has gone back to going to the moon first and then on to Mars. Personally, I'm a Mars guy, but I think that is the right thing to do from an operational perspective, because to answer the second part of your question, going to Mars is at minimum, 4 to 5 month trip one way. It depends on the exact launch window. Sometimes things are better aligned, and you have a launch window to Mars every 26 months. Some of them are better aligned, so it can take 4 or 5 months. Some of them it'll take 11 months. And if you're outside the window, you can launch and never get there. And then, the baseline mission is about 6 months on cruise, a year and a half on the surface, and 6 months to return. So, 2.5 year mission. So that's why I think, and this is, again, Mars is far away, so you don't have real-time communication with your astronauts. They're kind of on their own. Not completely, but you don't have real-time communication like we did on the moon. So I personally think that it's a good idea to go back to the moon just to figure out how to live for long durations in space. But yes, we are working towards how do we shield astronauts from radiation? How do we feed them when they're there? How do we keep the food supplies good? Can we grow food on Mars? How do we, what do we do? What do we need to do with life support? What are the power systems that we need? So yeah, there's a whole host of things that we're currently working on. Yeah.
So with that, do you see a collaboration with SpaceX possibly, or is that more of a competition?
No, it's definitely a collaboration. So I was at SpaceX 3 weeks ago, and SpaceX is really, really good at building rockets, right? And they're getting better at other things, but there is a whole host of things that SpaceX doesn't know that they rely on NASA to kind of fill in the gaps. And so this is where it's really collaborative. So they have, the technical term is, they have a non-reimbursable Space Act agreement where they can communicate with each other. And so the way that it works, like how I got involved with this, is somebody at SpaceX was like, hey, I want to talk to somebody about a Mars regolith simulant. So what's a good test material for Mars today? Like if we want to do test, what's a good material to use? I'm a Mars regolith simulant expert. So the NASA guys funnel it to me, and then I talk with SpaceX. So it's definitely a collaborative thing. Where I'm super excited about SpaceX is reducing the launch costs, because we have a lot of mass that we've got to throw to Mars. And the cheaper that is, the more likely it is that it'll ever happen. So it's definitely a cooperative thing. And here and then.
How much have you thought of trying to, so terraform isn't quite the right word, but just for example, if you were to chuck some really good bacteria at Mars and see if they could survive on the surface, have you ever thought of doing something like that?
Yeah. Well, have you ever read the Mars trilogy by Kim Stanley Robinson? It's a science fiction trilogy where they do exactly that. So first of all, right now that's illegal. So there's a treaty like the International Space Treaty or something like that, which establishes planetary protection protocols, which prohibits forward or back contamination from planet to planet. And the reason is, one is, so at some point in the distant 100-year future, maybe something like that. But the thing is, we have important scientific questions that we want to answer first, right? We want to know if there was a second genesis of life on Mars and if the biochemistry is the same. If we populate the entire planet with terrestrial bacteria, that experiment is toast. Right. So we have to, there are very stringent cleaning methods for anything we send to Mars to get down below some kind of organic carbon threshold, or then the bacterial load, the colony forming units per centimeter squared or whatever. There's very stringent thresholds. And then coming back, when we bring stuff back, we haven't yet, we want to bring stuff back from Mars to the Earth. We have to be very careful about how we handle it. You guys have probably at least heard of the Andromeda strain, right? This is something that is extremely unlikely, but it's one of these things that's okay, it's extremely unlikely, but the consequences of something bad happen are catastrophic. So let's at least think about it. So that is something that people think about, but in the context of there's things that we have to do first. But long term, if you want to talk about colonization or something, that's definitely something that we would do.
Okay, thanks.
questions? Yeah. How do things on Mars get their name? Yeah, so there's a couple different ways. The official way is you have to go through the International Astronomical Union, and they have some big, long process. The unofficial name is I name stuff on Mars all the time. Like we have like any rock that we take a picture of or anything that we zap with the laser, like those all get a name so that we can refer to it by a name rather than, oh, remember target 1,847? And the way that it works is we define these squares from orbit and gave the squares names, so they're named for like places on the Earth that are relevant to like mostly Precambrian, so billions of years ago. And then when you're inside that quad, you have a list of names that are relevant. They're like names of towns or formations on the Earth. But like I find like I named something after one of my kids or my sister. Like I'll send a picture like, hey, I named a rock after you on Mars today. But the bigger stuff, like the official stuff, has to go through this big, long, onerous process. But we do. I mean, some of the first ones, there's rocks on Mars named Yogi Bear and Scooby Doo, and all kinds of fun stuff. And it's also kind of fun. Or like we have some like Goldilocks, Dodo. So it's great. You're like reading a paper in science, like we analyzed the Dodo Goldilocks target. Like, just have to giggle a little bit about that. Or we give things like these. For a while, we were in a quad that was we were doing like sub-Saharan African names. That was fun. Nobody could pronounce any of them. Listening to the guys who were responsible to say it all the time was just hilarious. So yeah. Yep. Yeah, so this is why it's so hard. It takes 3 missions. You have one mission. So the next mission is called the 2020 rover. It's going to go and collect soil samples or core samples and put them in these little stainless steel tubes that are sealed, vacuum tight. And then it's just going to leave them there. And then another mission will come get them and bring them back to a little platform that has a rocket on it that will shoot that rocket with the samples shoots into space. And then it rendezvous with another mission that's been orbiting Mars that has a stage that can send it back to Earth. So this is why it's like a $10 billion thing that requires 3 to 4 missions over a period of 5 to 10 years. Yeah, yeah. If you had all the money in the world and everybody was like, yeah, we need this tomorrow, you could technically do it in like 4 years, but realistically it'll be like 10 to 15.
And also, why Mars? Why Mars as opposed to any other planets?
So Mars is the most Earth-like planet. Venus is you could say Earth's evil sister, where like the surface of Venus is hot enough to melt lead. And you have like sulfuric acid clouds and a 90 bar carbon dioxide atmosphere. The United States has never successfully landed something on Venus. We've never really tried. The Soviet Union, back when there was a Soviet Union, successfully landed 2 things on Venus that lasted for a couple minutes. So Venus is really, really hard. There are some moons in the outer solar system. There's a moon of Jupiter called Europa, and a couple moons around Saturn. One is Titan, the other is Enceladus. Europa and Enceladus in particular, they have an icy crust, and we know that they have a subsurface ocean. And Enceladus has a warm subsurface ocean, and it's constantly spewing stuff out into space. And so one potential mission that I was on that unfortunately didn't get selected yet, hopefully we will the next round, is fly to Europa, fly through these plumes of gas and dust that are being ejected from the ocean, and look for signs of life there. So there are other places, but Europa, getting to Europa is like a 3 to 4 year trip just to get there. Enceladus is the next planet out, or around the next planet out, so going even farther. So Mars is the closest and the most Earth-like, but there are definitely other places that we're looking to. Good question. Yeah.
You were talking about
So this gets into more of a philosophical, like me personally, I think that yes, that there was life, if not there, then on Mars. And the reason I think that, it's not just a total wish. The reason I think that is because the evidence for life on Earth is that as soon as life could exist on Earth, it did. Right? Like the oldest rocks that we find on Earth have evidence for life in them. So as far back as we can look on Earth, there is life. Some of the evidence is a little bit shaky, but most people agree with that. So that's the reason that I think that, we don't know how the origin of life works, but my personal thought is that because when it could happen on Earth, it did. If you have these places on Mars that had habitable conditions for millions to billions of years, why not? But that's why we're looking, right? So yeah, but great question. All right, yeah, one more, and then I'll be hanging around here. I'm happy to answer more questions.
With the upcoming InSight mission,
Uh-huh.
sending to Mars, what are the major differences between that and the rovers that they sent up?
So the question, there's a mission that's launching to Mars in 2 months called InSight, and that is actually looking at the interior of Mars. So it has a heat flow sensor and a seismometer. I think there's one more instrument, but it's all about the interior structure. So it's wanting to know where is the crust mantle boundary and the mantle core boundary and that kind of stuff. So it's important in that it tells you something about kind of like the overall history of the planet over billions of years, and it teaches us about planetary formation or whatever. But it's less directly related to habitability. Yeah, but I'm fingers crossed that everything works for them and that they get good data, because they're important questions to answer. It's a little bit further down the chain as far as habitability is concerned.
So they won't be taking any samples, or is it just?
Nope. No samples.
I just have an engineering question.
Yeah.
Because you've been there since 2010, you said?
12.
12. So you didn't design the instruments you're taking data from. So you're
Oh, me personally?
Right.
So I was involved with. So before the mission that landed before this one, was the Phoenix lander, and I was on that mission from like a month after it started until after it died. So I saw through the whole process. I'm not an engineer, but I worked with the engineers to help. Like the scientists give requirements, right? Like this instrument needs to be able to do this and this and this at this level of precision and accuracy or whatever. So I would work with the engineers to define the requirements and then test that they're meeting the requirements. I'm a little bit involved with the engineering side on the SAM instrument, where I look at I was involved before, so I was involved before it launched. I wasn't making big design decisions. It was more, again, about like verifying performance. But then now I'm involved with, I'm what's called a payload downlink lead. So when we get data back, I'm the first guy, at least when it's my shift, I'm the first guy to look at it and make sure that everything's good with the instrument and all the heaters and everything operated like they should or whatever. But yeah, so I've worked very closely with the engineers, and I've been involved with the mission from start to finish. But yeah, I'm not the guy designing the
Just
hardware.
wondering if you had to deal with the quirks of other people's ideas.
Oh, sure. Yes, definitely. Yeah. Yeah. Okay. And I think, yeah, if everybody's kind of going out, but come up and ask me your questions. I'm happy to talk to you. All right. Thank you.